Okay, this is a bit of a how-to video on graphing your data, transforming your data, doing a straight line graph, checking your work for the Physics 2.1 investigation. So doing the original graph. So we're starting with a table of data in a Google document. So this has already been collected and had an average created. We copy and paste the independent variable and put it in a spreadsheet. We copy and paste the dependent variable, paste it in here next to the independent variable. Now we copy and paste both columns. So we copy both columns rather. We open up a CODAP document and we do new from clipboard. This gives us our original data table into CODAP in a format that CODAP will be able to work with well. We now insert a graph. We expand the graph to fill a bit more of the screen space because we want a bigger graph rather than a smaller graph. We drag the independent variable onto the x-axis and the dependent variable onto the vertical axis. And now we change a few of the properties. So we change the point size down, change its color to black, just a good small but visible point size. And there is our graph. We're just going to give it a quick title. And the title, easiest one to use, is just vertical axis, that's distance, versus horizontal axis, in this case time. Okay, there's our graph done. We need a curved line of best fit. We're going to do that in our document. Now we take a snapshot using the snipping tool or equivalent, whatever platform you're working on. Right, so we come back here, we want to paste it in. We could just paste it, but we actually need a curved line on the graph. The best way to do this, most consistent way to do this, is to use the Google Drawing tool. So insert drawing, new, and now when this opens up, we're just going to paste it in here, and then we're going to add a curved line over the top. So we select the curved line tool, and actually a series of points, if you have the curved line tool, a series of points will create a nice smooth curve. You might need to use points that aren't on the line if your points don't nicely line up in a nice smooth curve. You don't want a wonky looking curve. Just one single smooth curve. In this case, that shows us the relationship, right? This shows us that the distance is proportional to time squared. So we're going to say from the graph, the distance is proportional to time squared. And we're going to put it in symbols as well, and then we're going to say D is, and then we're going to insert special character to get the proportional character. So go in here and write prop, and there it is. Proportional, oops, accidentally included a second one, proportional to t squared, and we're going to put it squared in by using control dot. That gives me superscript, and if you want to toggle back to standard characters, you can press control full stop again. So then we go on just to reinforce to myself what the point of the next part of it is. So this means that a graph of distance versus time squared should be linear. Time squared in that graph, well, time is measured in seconds, so time squared will be measured in seconds squared. So that knocks off 2 key points straight away in relation to merit, or at least one of the key points in relation to merit. I'm now giving the, actually 2. I'm telling you what variable I'm going to transform, and I'm telling you what the unit of that variable is. So that's pretty important. So now we're going to actually go and create that data. Now there's several ways to do this. One is to go back to a data table that you've already got, copy that data table down, and by hand work out time squared values. You'll need a column headed time squared, and then fill it full of values. Or you can go back to your spreadsheet and head a column up time squared, and put seconds squared, of course. In this case, you don't have the ability to use a superscript, so you're just going to have to use the little upper hat thing, up arrow. And then we've got a formula, so equals, and I can go and select that first cell of the time column, and equals a, that one star that one for squared, or that one, or 1 over that one or something. And then it's giving me an autofill suggestion for the rest of that column. So there we go, select that. Now I've got a set of squared data. I just did quickly check it by eye. Now we go and build the linear graph in CODAP. Now my suggestion, copy and paste the whole set of data. You only need 2 of these columns, but it doesn't matter. Having an extra column doesn't handicap you in CODAP at all. I am going to, however, create a new CODAP document rather than continuing with the one I had, because I just feel it's a little easier. So tables, new from clipboard. And let's just check my data carefully, maybe expand my table a little bit. No. Okay, insert a graph. Expand the size of the graph. Drag the time squared, that's your transformed independent variable, onto the x-axis, the horizontal axis. Drag your distance onto the vertical axis, so that's your dependent variable onto the vertical axis. Change the title, dependent variable distance versus transformed variable time squared. Okay, now go and change the point size again to something more realistic, and the color to black. And now, lucky last thing to do on this one is, well, this time we actually need a straight line of best fit, and CODAP can do that for us, including an equation if we select the least squared line. So there it is, and I'll just move that into a more convenient part of the graph. Now, this one we can paste directly into our document. We just have to use our snipping tool again, grab that, go back to our document, and paste it in. There it is, looking great. Now, one thing we need to do really is include a table of transformed data, and what we're going to do is just copy it from the spreadsheet and paste it in here. Now we want to fix this up a little bit. We're going to take the time squared column, paste it in here over the top of the time column, and then get rid of the time squared column by delete column. And then we're going to select the whole graph and go to our format menu, format table, table properties. I want to change the border because it seems to have lost the border somehow. It's not in that part of the menu, it's in the color, Logan. What are you doing? Here we go. Select black border. Good, done. Now, is that the table done? Not quite. I want to fix up the unit here where it had up arrow 2 and just give it the superscript 2 for seconds squared. That looks like that part of it is now done. All right, well, the next step is writing the merit conclusion, which is really a case of putting in all of the bits of the equation. So what we're going to do is we're going to start by pointing out that the straight line graph, the fact that it graphed as a straight line, proved that the distance was in fact proportional to time squared. That's what proportional means, that if you graph one against the other, they're going to give a straight line. So here we've got a straight line between distance and time squared values, therefore that proves that the distance is proportional to time squared. What we're going to do though is describe each of those variables in a bit more detail. In this case, it was the distance that a falling ball has fallen and the time that the ball has been falling. So the square of the time the ball has been falling. Now we're going to talk about the gradient. So the gradient of the line is 4.9, but 4.9 is not much good without some sort of scale. So what we've got to do is give it a unit, and the unit is the vertical axis unit divided by the horizontal axis unit. So that is meters, the vertical axis unit, divided by seconds squared, the horizontal axis unit. The equation for the line is, and we can give it in words, distance equals 4.9 times the time squared. We can also state it in symbols. D equals 4.9 times t squared. And this is where you see me make a mistake, which I will eventually come back and pick up when I'm going through my checking. I'm going to give this also a key. So where d is the distance the ball has fallen in meters, there's a typo, has fallen. And t is the time that the ball has been falling in seconds. So the key tells you what the symbols are, and it tells you what unit they're measured in, which is really crucial because those units affect the gradient that you get. That gradient only works if you measure in those units. Just going to tidy this up a little bit more by including the reference to it being now symbols. Okay. And all that's left now is a whole lot of checking. And do not neglect this. This is for merit. So I'm going to check all the stuff I've already done before I start writing my discussion. I might still find other things while I'm writing the discussion. So let's have a look. There's one of my data tables, had a quick skim over it, missed a few things. Checking the achieved graph and the achieved statement of the relationship. Checking that I've got the transformed unit correctly ascribed. What I'm going to do here is just put in the symbol for time squared. I don't know why, it's just to make it read better, seeing as I've got the unit in symbols as well. So I thought I'd put the variable in units there. Sorry, variable in symbols there. Check the straight line graph. Has it got everything it needs? Yes. Okay. Now I've found one of the things I like to check for is that the tables are consistent. So the data values in the tables should be given to the same sort of level of accuracy for all values. And one of the core things in this is that when you have your transform variable, that accuracy doesn't suddenly become incredibly overstated. In this case, they're still mostly to 3 significant figures, so that's all fine. Check my straight line graph, that looks good. Right, what else have I got? Let's see, do I eventually pick up? Oh yes, I finally pick up that I've missed out my equation. My symbol equation here is incorrect, and because it missed out the function. So d equals 4.9t squared, not 4.9t. And I picked up one more thing, that my measured distances in the first table should have all been given to the same number of significant figures as the others, because the ruler measured in millimeters, which is thousandths of a meter. Cool, there it is, absolutely complete and ready to do my discussion.